Okay, hello again. This is your instructor Ismail Badran for Chemistry 101, and today we are going to continue with chapter 3 on the chemical calculations. And last time we talked about the idea of mass percent, and I think now you are able to determine the mass percent of each element in a compound easily. The idea of the mass percent is important in order to determine the nature of the compounds, the structure of compounds for organic compounds. So the way we do this is we can burn a sample inside this reactor that you see in the picture, and from some calculations we can determine the empirical formula of that compound. If we are able to determine the empirical formula, in case we know the molar mass of the compound, we can determine the molecular formula of the compound. So this is part of what we call chemical analysis, okay? Before I start, if you ask me how to determine the molecular mass of compound, we can do that easily by mass spectrometry. You put the sample in a mass spectrometer and that will tell you the molar mass for the compound. But if you have a sample, let's say a sample that is shown here in yellow, okay, and you don't know the structure of that sample or the formula of that sample, you can burn it in oxygen, okay, in excess oxygen. That will form basically CO2 and H2O. We have in this furnace two kinds of absorbers. We have H2 absorber and we have CO2 absorber. So in this case, we can the H2O is formed. We can determine the grams or the mass of H2O that is formed, and also the mass of CO2. From this, we can calculate how much carbon we have, how much hydrogen, and how much oxygen is in the sample. So this apparatus, for example, it's for burning ethanol. And by burning ethanol, if you burn any organic compound, basically it's going to form CO2 and H2O. And we can use absorbers. That's simply chemical compounds. They can absorb H2O and CO2. Let's imagine that we are burning 11.5 grams of ethanol, and assuming that we don't know the structure of ethanol, okay? And this burning that 11.5 grams produces 22 grams of CO2 and 13.5 grams of H2O. Now we know already that ethanol contains H, C, and O, so three elements: hydrogen, oxygen, and carbon. The idea here is you can obtain first the grams of hydrogens in the ethanol sample from H2O, from the water. You can determine the grams of carbon from the CO2, okay? Because where else the carbon comes from? It's from the sample, right? Okay, so the way this works is you bring a sample, an organic compound. Usually it has carbon, hydrogen, oxygen, maybe other elements like nitrogen. So you can know the elements in this sample by using something called elemental analysis. And then you burn this in oxygen. That's going to form your CO2 and H2O. And you do this in a closed system, okay? So there is no other source for carbon or hydrogen or elements except the sample. So the sample, the source of carbon here in the CO2, the source of carbon is going to come from the sample. Where else it's going to come from? There is only the sample in the machine, in the instrument, and any carbon is formed in the CO2 is going to come up from the sample. And similarly here, the hydrogen that is in the water, it's also coming from the sample, right? There is nothing else this hydrogen can come from. There is a problem with the oxygen because you are putting excess oxygen anyway. So it's very difficult to deal with oxygen. But we can at least know how much carbon that we have. Let's say here I'm forming, let's say, 10 grams of CO2. And I have, let's say, I'm forming 20 grams of H2O. From that, I can determine how much carbon I have in terms of mass. Okay, I can find how much mass of hydrogen I have. Okay, and from that, I can convert that into number of moles. I can do that, number of moles of carbon, and I can convert that also to number of moles of hydrogen. And you know how to do that. You know how to find the empirical formula from this. If you know the molar mass of the compound, in case you know the molar mass of the original compound, or at least a guess of the molar mass, you can find the molecular formula. Okay? Now, sometimes what complicates things is that you have oxygen in the sample. If you have oxygen in the sample, we can still figure this out, as I'm going to show you in this example here. Let's imagine that we are burning 11.5 grams of ethanol. Ethanol contains 3 of them, H, C, and O on it, okay? This produces 22 grams of CO2 and 13.5 grams of H2 as an example, okay? So the way we do this, first we take the CO2, the grams of CO2, we convert it to moles of CO2, and using the idea of mass percent, as we taught you before, we can figure out the moles of carbon, right? Because we know that we can use the idea of mass percent to find the moles of carbon, and then we can convert that to grams of carbon. So now we have, so what I'm going to do here, I'm going to use the idea of the mass percent to figure out what is the mass of carbon in the sample. Now remember that the mass percent of carbon in CO2 is equal 12 divided by 44, because the molar mass of CO2 is 44 and the atomic mass of carbon is 12, so that's the mass percent. The nice thing about the mass percent is you can multiply it by any grams, by any mass, and that will give you the mass of that element. So in this case, I say the mass of carbon, not the mass percent, but the mass of carbon in CO2. So in this case, I will say the mass of carbon, okay, in CO2 is equal to 12 divided by 44. Let me just do it like that. 12 divided by 44 times the mass, which is 22 grams. This is easy mathematics. The 22 goes with the 44, leaves 2, and this will give you 6 grams. Now let me do that for hydrogen in water. This is the same thing. Let's use that concept to apply for hydrogen. Now here I have 13.5 grams of water. Now in this case, mass of hydrogen in water, it's equal to the mass percent of hydrogen in water, which is in this case 2 divided by 18. We did this last time, the mass percent of hydrogen in water. It's times, now you can put the grams, which is 13.5 grams. That's the mass of water. If you do the mathematics for that, it would be 1.5 grams. That's good. Now we have mass of carbons, mass of hydrogen. You can proceed and find the empirical formula. The only problem that we have is that we have oxygen in the sample. We have oxygen in the sample. The sample is 11.5 grams. 6 grams of them is carbon. 1.5 grams of them is hydrogen. You can tell that there is still some space for oxygen, so you can calculate that. So you say the mass of oxygen. This is the smart idea. You cannot calculate, you are not able to calculate the amount of oxygen from CO2 and H2O. You never do that, because remember, there is excess oxygen that we are adding. So the only way to do it is you do it by subtraction. You know the sample that contains the 3 elements, so in this case the mass of oxygen will equal to the mass of the sample minus whatever mass of H plus mass of C that you have. In this case, the mass of sample is 11.5 minus, you have 6 for the carbon plus 1.5, and if you do the math, that would be 4 grams of oxygen. That's good. Now we are done with this. So going back to my slides, you see here, I figured out how many grams of carbon I have, 6 grams, 1.5 grams, and 4 grams. And now you can figure out the empirical formula. You just change that into moles. So 6 divided by 12 is half, 1.5 grams divided by 1 is 1.5, and the grams of oxygen is 4, therefore divided by the atomic mass of oxygen, which is 16, that will give you 0.25. That should give you C half H1.5 0.25 as an initial formula. You divide by the smallest subscript, in this case 0.25, and therefore the empirical formula for this compound, for ethanol, is C2H6O. it's a coincidence that this empirical formula is actually the same as the molecular formula, but that's not the same all the time. Okay, that's not the same all the time. But in this case, it worked. We have an empirical formula that is the same as the molecular formula, and we are good. To practice this, I have another question here that says cumin is a compound containing only carbon and hydrogen. This is an easier question because the sample has only carbon and hydrogen, and there is no oxygen, which makes our life a little bit easier. So cumin is used in the production of acetone and phenol in the chemical industry. Combustion of 47.6 cumin, so that's a sample, it's 47.6, produces some CO2 and 42.8 grams of water. He's not giving you how much CO2 is producing, but we will still able to solve this question. Okay, and the molar mass of cumin is between 115 and 125 grams per mole. That's good. He's giving you kind of an idea what is the molar mass of cumin. Determine the empirical and molecular formulas. So here I have wrote the equation. I said cumin plus some oxygen because we are burning this. It's going to form CO2 and H2O. I have 42.8 grams of water. I'm burning 47.6 grams of cumin. I have no information about CO2. And he said the molar mass of cumin is about somewhere between 115 and 125. We're going to use this piece of information at the end of the question. But again, the way I do this question, from the grams of H2O, I can figure out the number of moles of H2O. So to solve this question, I can use the grams of H2O that is given me to figure out the grams of H that I have in the sample, and from that I can know the number of moles of H in the sample. Now what about the number of moles of carbon? Can I get it from CO2? Well, he's not giving me any information about CO2. But since the sample contains only carbon and hydrogen, as he said, and he said in the question that this sample is only CH, there is no oxygen, I can use subtraction to do that. So let me show you how. First, I say the mass of oxygen, mass of hydrogen in the sample, NH2O, first, is equal to the mass percent. In this case, it's 2 over 18 because hydrogen in water is 2. That's the idea of the mass percent, times the mass of water, which is 42.8. 42.8 gram. And if you do the math, that will give you 4.75. I would say 4.647 gram of hydrogen. Okay. So, and here's the idea: is that the mass of H in H2O, it's 4.780 gram. That is equal. That's equal to the mass of hydrogen in the sample. In cumin. Watch this. We just calculated how much hydrogen we have. We have around 4 grams. This hydrogen is the same as in the cumin because we are burning cumin in a closed container. Where else hydrogen is going to come from? It's going to only come from the sample. So whatever hydrogen in the water, that's the 4 grams we just calculated, it's from cumin. But the cumin is 47.6 grams, so the rest will be carbon. You get the idea? There is no need here to give you any information about CO2. We just can calculate that from the water. So in this case, we say the mass of carbon, it's equal to the mass of sample, which is 47.6 grams, minus those 4.76 grams. And that will give you a lot. That will give you 42.84 grams of carbon. That's good. Now we have so that's good. Now we have mass of hydrogen, mass of carbon. We can find the empirical formula from these two easily. So I want to convert that to moles. I can do this here if you like. So that will actually equal to that's going to be the same 478 mole of hydrogen because you divide by 1. This one you divided by 12, so 48.84 divided by 12, that's going to give you 3.57. 3.57 mole of carbon. That's good. Then you come here and you say that's going to be C 3.57 H 4.78. That does not look like a good empirical formula. You cannot, of course, round here. You have to divide by the smallest subscript, which is 3.57 in this case. That will give you C1H and then 4.78 divided by 3.57, and that should give you something like C1H 1 point something. It's 1.3. That will give you 1.34. And now we have an empirical formula. It's a finicky empirical formula. So the only way to do this, you have to multiply by something, as we did in one of the questions. If you multiply by 2, that's not going to work, because that will give you C2H maybe 2.6. If you multiply this by 3, that will give you C3H 1.34 times, that's kind of around 4. So this is the empirical formula for this compound. Now the question is, how much is the molar mass for this? What is the molar mass of the empirical formula? You can do that easily. 3 times 12 plus 4, that would be 40. 3 times 12 is 36 plus 4 is, so it's 40 grams per mole. So now you get the idea. If you take a look here at the beginning of the question, he said the molar mass of cumin is between 112 and 125. So this is not cumin. This is the empirical formula for cumin. So I want to bring this number to something in between 115 to 125. Do I multiply by 2? If I multiply by 2, that's going to be 80. If I multiply by 3, you must multiply by whole numbers, okay? To go from empirical formula to molecular formula, you must multiply by whole numbers. So 40 times 3 is 120 a gram per mole, which fits within this range. That means cumin is actually C9H. 4 times 3 is 12. That's cumin. Okay? And to double check that, you just Google cumin. Let's say molar mass. You can you have internet access all at home. Oh wow, 120.19 gram per mole. That is cumin, and this is the C9H12. Okay, we already got it. So this is how you solve this question. And here's another question that says a sample of compounds contain 30.46% nitrogen and 69.54% oxygen by mass, as determined by a mass spectrometer. You see here we can use also some mass spectrometer to determine these ratios. The molar mass of the compound is found to be between 90 and 95. Determine the molecular formula and the accurate molar mass of this compound. This question is easier than the previous one. Let's write what is given. Here we have 30.46% of nitrogen. We have 69.54% oxygen. So that's not a number of moles, neither grams, it's percent, okay? So he said find the molecular formula and the accurate molar mass of this compound, given the fact that it's between 90 and 95. The best way to solve this question is that we can assume that we have, in this case, if you have 100 grams, that means we have 30.46 grams of nitrogen and have 69.5 grams of oxygen. You see that? That's now you know what to do. You need to convert that into a number of moles. You convert that to a number of moles, and from this you obtain the empirical formula. So the number of moles of nitrogen in this case, it's equal 30 divided by 46 divided by 14. Number of moles of oxygen would be equal 69 divided by 54 divided by 16. Okay, so if you do the math, that should give you a number of moles of nitrogen is around 2.175, and the number of moles of oxygen is 4.35. So the initial formula for that would be 2.175, and then oxygen is, sorry, that should be capital N. Oxygen 4.35, and this, of course, as we always do, we divide it by the smallest ratios, and that will give you N1O 4.35 divided by 2.175, and that should give you NO2, and that is the empirical formula. Again, the question is, what is the molar mass of the empirical formula? Because we need to see if this compound is right or not. So the molar mass of the empirical formula is equal to 14, because nitrogen is 14 plus 16 times 2, so 32 plus 14 is 46 gram per mole. But in the question it says the compound is between 90 and 95 gram per mole. Okay, there's a typo in the question. It says gram per, it should say gram per mole, not a gram. So 46, that doesn't sound good. We need to get into this between 90 and 94 gram per mole, because he said the molar mass of the compound is between 90 and 95. So clearly we can here multiply by 2. Again, you need to multiply by whole numbers if you want to go from empirical formula to molecular formula. 46 times 2, that would be 92 gram per mole. And therefore, we multiply the empirical formula by 2. We have NO2, that's N2O4, is the molecular formula of the compound. And the accurate molar mass is 92 gram per mole. That's N2O4, that's the question. Does anybody know how to balance this equation? Or is this equation already balanced? Anybody?
No.
Yeah, okay, so, yeah. So, what should we do? Yes? 2HF, yes. So, this is balancing equation. Some of you, so today we are going to talk about balancing equations and solve chemical problems. So, I want you here to pay attention with me on how to just introduce this. Let's assume that we have 100 grams of this, okay? And the question says, how many grams are we going to produce out of this? Okay, this is the question. So let's assume, my friends, that here we have an equation that says H2 plus F2 goes to 2HF, okay? And the 2 is part of the question because it has to be balanced. And now it says I have 100 grams of H2. How many grams of HF I'm going to produce? The wrong way to solve this question, of course, is to do this. Is to say, okay, from the equation, I know 1 mole of H2, I say 1 gram of H2 will produce 2 grams of HF. That means 100 grams of H2, then will produce 200 grams of HF. This is wrong. This is all wrong, okay? You don't do this in chemistry, because we don't deal with the grams. This equation is at the top, H2 plus F2 goes to 2HF. It reads 1 mole of H2 plus 1 mole of F2 goes to 2 moles of HF. Therefore, you cannot do this in chemistry, dealing with the grams. So the way you do this is you have to convert the 100 grams into moles, and then you do the math. Anybody calculated the molar mass of H2? What is the molar mass of H2?
2.
Yes, 2 grams per mole, right? This is 2 grams per mole. And the HF is, you have, the H is 1 and F is 19, so this is 20 grams per mole. Okay? If you go to the periodic table, you find F is 19. So the way you do this, my friends, is the best way to do it is you go from the grams of hydrogens, you convert that to moles of hydrogens. N means number of moles. And then from that you can calculate the number of moles of F2, and from that you can calculate the grams of F2. So you can do it. You can do it either unit analysis or using formulas. Let's first do it the school way, the way that you learned in school. And the number of moles of H2 equals mass divided by molar mass, right? I have 100 grams divided by 2, that's 50 moles. So now I found the number of moles.
right? Then I do kind of a proportion as you learned in school, but not with the grams, but with moles. I know from the equation here that 1 mole of hydrogen produces 2 moles of HF. Can I say that? 1 mole of hydrogen gas will produce 2 moles of HF. Now where did I get this from? I get it from the equation, okay? This is from the equation. This is the symbol for equation. EQM means equation. But I don't have 1 mole, I have 50 moles. Here, I calculate that I have 50 moles. The 100 grams is 50 moles. So I say 50 moles of H2 will produce X. Okay? And then you do it as you learned in school. You cross multiply this. So X, which is the number of moles of HF, will equal to this times this divided by 1. So 2 times 50. So you have 100 moles of HF. The question is, he says, I need the grams, right? So we convert that to grams. So then, you know the number of moles equals mass divided by molar mass. In that case, the mass of HF is equal number of moles times the molar mass, which is equal the 100 moles times the molar mass of HF. We said 20 gram per mole. This goes with this. That means we are forming how much? 20 times 200, that's 2,000 grams of HF. 2,000 grams. Exactly. 100 moles times 20, 2,000. See? That's a lot of grams. So it's not 200 grams, it's 2,000 grams. So I'm just going to zoom out and allow you to copy this. However, this is not the recommended method to do it in chemistry in the university. We have to do it now using unit analysis, because in unit analysis it's much faster and it's much easier. So let's call this method A. That's the school way. Now in method B, we're going to use unit analysis. You can do it method A, but I don't like it. In method B, you stick to your plan, gram of H2. You see, you take this is your plan, right? This was your plan. Grams of H2, you convert it to number of moles of H2, and then to go to number. You see, you do that. In unit analysis, it's much easier. You say, what is required? He needs the mass of HF. And it's equal to. He's only giving you one thing, which is the 100 grams of hydrogen gas. So you put that, and then you start multiplying. In unit analysis, we only multiply by factors. According to your plan, you want to change that into moles, so it's very easy. You say 1 mole of H2 is 2 grams of H2. شايفين؟ سهلة جدا. So this one goes with this one. And then you carry on with multiplication. Now you need to bring something called the molar ratio, because this is 1 mole of H2 and I want to change it to 1 mole of HF. So I multiply by a molar ratio, then you go and take a look at your equation. What is the relationship between H2 and HF? It's 1 to 2. So you write this down. So here it does make sense that you say 1 mole of H2 corresponds to 2 moles of HF. Where did I get this from? This is called the molar ratio. Don't forget this. You have to put it in your molar ratio, okay? So now this moles of H2 goes with this. Oh, now I have moles of HF. Very good. So I just changed that into mass. So multiplied by, I know how to change that. I did it many times. So I know that 1 mole of HF is equal to 20 grams of HF. Then this one goes with this one. Oh wow, and you see, that's the nice thing about unit analysis, is this also 2 grams, is this 2 goes with this 2, they cancel out. Then you just multiply what? You just multiply 100 times 2 times 20, and you get the answer right away. It's 2,000 grams. See, one shot, you do it in one shot. 2,000 grams of HF is the answer. When you want to balance chemical equations, you want to write the correct formula for the reactants on the left side and the correct formula for the products on the right side. So that's why we taught you in chapter 2 how to name things. For example, when I say lithium chloride, you say LiCl, not LiCl2, for example, or anything else. And then you put all the reactants to the left and all the products to the right, and then you change the numbers in the front of the formulas. We call them the coefficients. This one, the one we started with, the 2, remember at the beginning? This is called the coefficient. When I gave you this equation at the beginning and I said balance it, and you said 2, this 2 before the HF or in front of the HF, it's called a coefficient, معامل. So you can change the coefficients to make the number of atoms of each element the same on both sides, but don't change the subscripts. That's very important that you don't change the subscripts. So for example, C2H6 plus O2 goes to CO2 plus water. If you want to balance this, you can put numbers before the formulas. You can say 2O2 or 3O2 or 4 or whatever. But you cannot change that from O2, you make it O3. That's changing the compound. You cannot do that in chemistry. Or H2O, you make it H2O2. No, you're not allowed to do that. Because in this way you are changing the compound. But you can put numbers before the things. Now, how do you balance equations? Let's take an example. This one. C2H6 plus O2 goes to CO2 plus H2O. The best thing is to start an element by element. And you start by balancing those elements that appears in only one reactant and one product. Look at this equation. C2H6 plus O2 goes to CO2 plus H2O. We have carbon, we have hydrogen, and we have oxygen. And the best thing here to do is to start with an element that it is easy. It appears only once in the left and once in the right, which is carbon in this case. You start with carbon here. We have 2 carbon atoms to the left, but we have 1 carbon atom to the right. So this equation is not balanced. So any idea how to balance the carbon? We can multiply the CO2 by 2 to make the carbons the same. See, you have 2 carbons on the left, we have 1 carbon to the right. So the best thing, we multiply the CO2 by 2. We do it step by step. So now the equation is this. Now the carbons are balanced, but the oxygens and hydrogens are not. Now we move on to the hydrogens. We have 6 hydrogens here to the left. We only have 2 hydrogens to the right. So the best thing to do is we multiply the H2O by 3. So now the equation becomes like that. Now the hydrogens and carbons are balanced. Now we need to move on to the oxygens. Okay? How many oxygens do you have here? We have 2. If you count the oxygens to the right, we have 4 and 1. Sorry, 4 and 3 is 7, right? So these are not balanced. So the best way to do it is to multiply the oxygens by 7 divided by 2. So the equation is balanced now. So this is a balanced equation, but the problem with it is that it's balanced with fractions. And sometimes in the question, it says balance this equation using whole numbers. لازم تكون أعداد صحيحة. So in this case, we have to multiply this whole equation by 2, and the equation becomes as 2C2H6 plus 7O2 goes to 4CO2 plus 6H2O. So this is an equation that is balanced, and of course you double check and everything is okay. I want you to pay attention to this here, fit.com. This is a very nice website. See, this is fit.com. It's a very interactive, nice simulation. And then please play with this at home, okay? Take this for, oh nice, see, now he's giving you this, and you can play with this to balance the equation. And the tools, you can use this or that, or let's use that. You see, this is not balanced, and then, I don't know, you play with this, I don't know, it's not balancing. So when you go home, I mean, you are home anyway. When you have free time, please use this to learn how to balance equations. This example, my friend says that when aluminum metal is exposed to air, a protective layer of aluminum oxide forms on the surface. The layer prevents further reaction between aluminum and oxygen, and it is the reason that aluminum beverages cans do not corrode. In this case, in the case of iron, the rust, which is iron oxide, that forms is too porous to protect the iron metal underneath, so rusting continues. Write a balanced equation for the formation of aluminum oxide. Before we solve this question, let me tell you something about aluminum. A question arises why we don't make food beverages or Coca-Cola cans, let's say, from iron. If you have something that made of iron, okay, iron oxidizes. and forms iron oxide. So let's say this is iron, Fe. So Fe reacts with air and it forms rust, صدى, بصد يعني. It forms a layer here of rust. Okay? So this is rust. اللي هو الصدى. اللي هو Fe2O3. The problem, we have oxygen here. The problem with this Fe2O3, it's porous. It allows oxygen to get in, and so this whole thing, after sometimes it rusts. Okay? This whole thing becomes rust. يعني كله بصدي. And that's why if you leave something that is made of iron, a car or a can or anything, and for some time, a month or two, it will rust. But that does not happen in aluminum. This is different in aluminum. The story is different in aluminum. If you have a can or something that is made of aluminum, a window or anything, okay? Aluminum also rusts. It makes aluminum oxide, okay? So this is a layer here, a thin layer of aluminum oxide. Okay? But this layer prevents oxygen from getting in. If you have oxygen, it cannot get inside. خلاص بوقف, it stops here. So actually it protects the rest of aluminum from oxidizing. And that's the nice thing about aluminum. So aluminum rusts, and actually it rusts faster than iron. But the nice thing about it is this layer, the L2O3, it does not allow aluminum from further oxidizing. So that's what the question here is talking. That's not the question anyway. The question says, write a balanced equation for the formation of aluminum oxide. I want to give you 1 minute, please everyone, to think about the equation of the formation of aluminum oxide from aluminum and oxygen. And of course a balanced equation. I will give you 1 minute to do that. And if you know the answer, raise your hands please. So you have aluminum metal reacting with oxygen to form aluminum oxide. I want you to write in your papers there at home a balanced equation for this. I will give you 1 minute. If you know the answer, please raise your hand. The first thing, guys, you do this equation, you start with Al. Now we have 2 atoms of Al. You cannot do this. This is not allowed. So you multiply this by 2. Okay, so that's the first step. And now you have 2 atoms of oxygen. You have 3 atoms of oxygen. So the way you want to balance this, you want to think about a number that you put here to balance the oxygens. What number is it? Is it 3/2? Right? Now this is a balanced equation. This is the balanced equation. 2Al plus 1.5 O2 goes to Al2O3. ممتاز. Because 1.5 times 2 is 3. If you multiply this by 2, 1.5 ضرب 2 3. وعندك 3 ممتاز. But this one is not. This one is balanced. But to make it whole numbers, you multiply the whole thing by 2. So the equation becomes 4Al, right, Najwa? Plus 2 times 3/2 is 3O2 goes to 2Al2O3. This is the answer for the question. So please write this down in your notebook. But now let's take this example and answer based on what I explained before. But people, now I'm gonna use the unit analysis. Okay, you can do whatever unit, because the exam is multiple choice questions. You can use whatever method you learned in school or after school. But for me, I'm gonna use unit analysis or dimension analysis, and I encourage you also to do it. Okay, deal? This question says the food we eat is degraded or broken down in our bodies to provide energy for growth and function. Of course, this story does not interest us. A general overall equation for this very complex process represents the degradation of glucose to carbon dioxide and water. So this is what your body does all the time. It burns the glucose. It eats food, you eat food, and you burn it to make energy. And of course, you produce CO2 with the process, and that's why you exhale that CO2 out. So he's given you a nice and balanced equation. This equation looks balanced to me, because if you check here, 6 carbons, we have 6 carbons, you have 12 hydrogens to the left, and you have 12 hydrogens. Yeah, it looks balanced. And now it says if 856 grams of glucose is consumed by a person over a period of time, what is the mass of CO2 produced? This is a straightforward question. No worries about it. Let's solve it together, okay? So open a new blackboard. Let's do it together. The first thing, let's copy the equation. I want everyone to prepare your calculators, please. And we'll do this question together. You at home and me here. Plus 6O2 goes to 6CO2 plus 6H2. Please write the equation in a piece of paper. Fire up your calculators. Okay? So we can do this together. The question says we have 856 grams of glucose, and it is what is the mass of CO2 produced? Here is the mass. That's it. This is the question. So this question is only between glucose and CO2. This and this do not bother us. This, the oxygen and the water, are not part of the question, so you don't worry about them. In the next lecture, they will be part of the problem, and I'm going to show you how to solve these problems. That's another story. There is limiting and excess and that thing and that. It's the first thing. You calculate the molar mass and you make sure it is right. If you screw the molar mass, if you make it wrong, if you get it wrong, the whole question will be wrong, unfortunately. So make sure to get your molar masses right. 180 gram per mole, and this one is 44. And here, this 6, we don't worry about it now. Okay? We just calculate the molar mass for CO2. Carbon is 12. Oxygen is 16. 16 times 2 is 32, and 12 is 44. The 6 comes later. For now, this guy and this guy, we don't worry about it, because he's not mentioning anything in the question about him, so we're fine. So now I'm going to proceed like this. He wants, so my plan, first is my plan. This is my answer solution. This is the abbreviation for solution. So he wants the mass of, you need the mass of CO2. I can get this from the number of moles of CO2. There is no way but to get it from the number of moles of glucose. Let's refer to glucose by G now. And I can get this from the mass of glucose. Sounds like a plan, right? In English we say, sounds like a plan. So he wants the mass of CO2. There is no way but to get it from the number of moles of CO2. Where are you going to get this from? You want to get it from the number of moles of glucose. So this is your plan. So this is the plan. Okay? You should say here, the plan here. It should be there. So the answer should be, using a unit analysis, you start what is required. What does he want? He say the mass of CO2, and then you write equal. He's only giving you one thing, which is 856 grams of glucose, and then you start multiplying. Okay, easy peasy. How many significant figures are in 856? There are 3 significant figures. So your final answer should be only 3. Remember this. It does make sense here to change this into moles. I know that 1 mole of glucose is 180 grams of glucose. Is there anything wrong of what I did? Or shall I continue?
You have to change it like
Very,
1 mole.
very good.
Over
1 mole should be in the top? Yeah, صحيح, ممتاز.
Yes.
So, okay, some people are awake. Very good. Nice. Yes, you're right. I need the 180 gram to be in the glucose, okay? And اكتبوا glucose خلاص. 180 gram of glucose is 1 mole. Yes, you're right. في ناس صاحيين. Glucose, okay? So now this grams goes with this grams. Okay, times. Sorry, my writing is not very nice because I'm using a pen. So now what? I need the molar ratio. Remember this. I need now the molar ratio between glucose and CO2. What is it? It's 1 to 6. 1 mole of glucose is 6 mole of CO2. So it does make sense here to say 1 mole of glucose is equivalent to 6 moles of CO2. You see? This is your molar ratio. You don't have to do this in the exam, but here I'm just showing you. Where did we get this? We get it from the equation. So nice. Now this moles of glucose goes with this. Very good. Now we are in moles of CO2. So we are just one step away from, I know that 1 mole of CO2 is 44 grams. Right? So now this goes away with this. They go home, and now the rest is mathematics. What do you think about this answer, my friends? How many significant figures are there? There are 5. And how many are here? You have 3. So this is not an acceptable answer. What do you think the acceptable answer should be?
1260.
1260 grams. Yes, you're right. Or you can write it down as 1.26 times 10 to the power 3. All alkali metals react with water to produce hydrogen gas and the corresponding alkali metal hydroxide. Li plus H2 gas. Very good. So this is the equation. He says how many grams of lithium. So the mass here is a question mark, right? Is he giving me anything? 9.89 gram. Okay, so 9.89 gram of this. Oh, nice. So this question is a two-party question. Remember this for next lecture. This is two-party question. Why? Because there are 2 things involved. This thing here and this thing does not interest us, and we don't worry about it, okay? Next time maybe we worry about it. But for this question, we don't worry about it. We have only H2 and Li. The molar mass of H2, it's 2 grams per mole. Lithium, you go to the periodic table. Where is the periodic table? It's right here. You zoom into lithium. What is the atomic mass of lithium? We have 2 numbers, 3 and 6.941. Which one we use? Yes, we use the atomic mass, 6.941. So here 6.941. Let's now use the correct one to get the answer right. This 2, you don't worry about it for now. It's gonna come up in the unit analysis. You see here in the previous question, when I said CO2, I calculated the molar mass to be 44. I didn't worry about the 6, but the 6 came up in the answer. You see that? This is how I implement my coefficients into the answer. And same thing here. The lithium is 6.941. You don't multiply that by 2, but the 2 will come later, okay? And the other thing is that people, they make mistakes in the exam. They use the atomic number, which is a 3 instead of the atomic mass. So be careful to use the correct one. Good. So now that's it. He needs the mass of lithium. The plan is he needs the mass of lithium. I can get that from the number of moles of lithium. There is no way but to get that from the number of moles of hydrogen. And I can use the mass of hydrogen to do that. Sounds like a plan, right? So let's do it. Then analysis, he needs the mass of lithium. So mass of lithium equals, you always start with what is required or what is asked for. He's only giving you one number, which is 9.98 gram. So let's use that and start multiplying. Start multiplying by what? If you are confused, go to your plan. Here is mass of hydrogen. We need to convert that to number of moles of hydrogen. So you know how to do that. You say 1 mole of H2 is 1 gram H2, right? No? Yes?
No.
This is all wrong. Why?
Grams should be at the bottom.
Gram should be in bottom. And also 1 mole of H2 is not 1 gram. Yeah, you're ممتاز. في ناس صاحيين. So yes. So the correct thing is to say 1 mole of H2 is 2. ما انت حسبتها هي 2 grams. 2 grams of H2. يعني هذا شايفه انت هاي اللي هون هاي بس بتحطها هون صح؟ Now next, and you can cancel this with this. And next, by the way, in the exam, guys, don't cancel. Don't do this, so the teacher can see what you are doing. In the exam, if you start doing this, your answer would look very dirty. Don't do the cancellations in the exam. Just I'm showing you here the cancellations for you because we are in a lecture, but in the exam don't do it. Next is the molar ratio between the two. I know that it's between lithium and so it's 1 to 2. So I have here 1 mole of H2 corresponds to 2 moles of lithium. That's from the equation. That's my, so the moles of H2 goes with the moles of H2 times, now left, finally I want to convert that to molar mass. So 1 mole of lithium is 6.941 gram. So you see the nice thing is that this 2 goes with this 2. That's the nice thing about unit analysis, okay? And also, as I said, the coefficient, it's implemented in your answer here. See, this is how I implement the coefficient. That's it. So you just multiply 9.8998 times 6.941. That's it. See, easy. This is the nice thing I love about unit analysis, is that it simplifies things. So 9